Okay, so let me check. Can you see me? I think you can. Okay. So, it's also sorry for taking time to make things work. Well, it was working just a few minutes before, but somehow. Okay, so let's get started. So this is what we are gonna do today. So don't forget about this one. So I thought I may be arriving a little bit late today, but fortunately it didn't happen. So today's topic is gonna be divide and conquer, which is somewhat different from what we've been mainly discussing before. So we've been mainly discussing only about the performance. So this is a little bit different topic, but yeah, the end of the semester approaching, I just wanna get into this before we finish. Hopefully you have some time working on this new notebook, which is about this divide and conquer. But before we start, so I made an announcement and a few video clips during the holiday. So once again, I apologize for the very late announcement of the how to get the credit, but everything I just announced during the holiday somehow related to this credit. So I guess you have already seen this, but just in case. So here's how you get the credit. So you should have submitted programming exercise assignments. And the other one is a final report, which I announced details about during the holiday. Abstract is basically just a declaration of what you will be doing for the final report, and its due is already a few days ago. So, but just in case you somehow missed everything and still want to submit the final report, I would just say this. But basically, it seems that many of you have already gotten this. And the final due is February 11th. And like I explained in details in the video, so there are two options. One is option one, which is basically about optimizing the performance of predefined problems, so which is neural network. And I already gave a baseline code, which took me a long time to prepare. And the other option is solve your own problems. And you have already decided which to work on by submitting this abstract, but just in case you have missed everything. So, so this is today's topic, which is divide and conquer. So let me get started. So yeah, like I said, this is basically the divide and conquer. But the underlying theme is how to solve complex problems in parallel. And this is what I'm going to cover today, so introduction. And I'll discuss one specific example in somewhat deeply. And how do you parallelize divide and conquer algorithms, and how to reason about the speed up. So let me start with the introduction. So why I'm speaking about this? So in this lecture, so the of course the underlying topic is of course parallel programming, but of course it's about getting performance. So this is what we have been focusing on so far in this course. But in terms of how you get the correct parallel algorithm, well, actually the problems we have been talking about is somewhat very simple one. So for example, matrix multiplication. There are something else. So it's sparse matrix vector multiplication. But when it comes to the question of how you actually get a parallel algorithm that at least works, but there was no issue almost at all, right? So just have a simple for loop or whatever. So in this sense, we've been almost solely focused on performance aspect, right? But actually there are algorithms, a parallelization of which is not trivial at all. So how to actually parallelize this algorithm is far from trivial, and especially only with the simple for loop or CUDA kernel launches, we cannot comfortably parallelize. So there are so many such algorithms. So divide and conquer is a very important concept, not only for parallelization, but also for something more basic. So here's today's conceptual goals. So one is to understand and appreciate the power of divide and conquer paradigm. Combined with task parallelism, which is a very suitable method for parallelizing such algorithms. So we discuss it with concrete examples and some exercise. Of course, the one topic is how, so given the divide and conquer algorithms, how to write task parallel programs, and how to parallelize it using task parallel primitives. So which we've already discussed before. So OpenMP task parallelism. But this is basically a review of OpenMP task parallelism. And somewhat more fundamentally and importantly, how to reason about the speed up task parallel programs. It's not as straightforward as reasoning about the speed up of very simple flat loop parallelism. So for example, just a single for loop or just a single kernel launch. So along the way, I'm going to introduce very important notions of the work and critical path and something called greedy scheduler theory. So this is the goal of today's talk. So let me get started with the very basic. So what is divide and conquer algorithms anyway? So perhaps it's the most the single most important design paradigm of algorithms. So it's not necessarily about the specific algorithm. It is a class of algorithms. So the basic idea is, so given a problem instance, so just think of it as a input size or the input data. So if the input is trivially small, so small that solving it is very trivial, then you just do it. And otherwise, so in this divide and conquer paradigm, you divide the original input or the problem instance into several sub-problems. Well, this step is typically called a divide. So you get several problem instances, each of which should be smaller than the original input. And you solve each of them independently. And you get partial results for each of these problems, sub-problems. And you somehow combine these sub-results into the result of the entire input data set. So this kind of pattern appears in many algorithms in many problems. And in terms of the the whole structure, it's solving a problem with a divide and conquer paradigm or algorithm results in a tree structure like this. So this is the original input. And you divide it into several subproblems. And each of these subproblems is then divided into even smaller subproblems until the problem becomes trivial to solve. So this is what is commonly known as the divide and conquer algorithms. So why it's important? So there's several benefits of mastering the idea of divide and conquer thinking. So many of them do not have anything to do with parallelization. Well, in a sense, it's important, even if you are not interested in parallelization at all. So divide and conquer paradigm so often helps you come up with an algorithm of a problem that is not known to you. So you are given a problem, so you just ask to solve this. So ask to write a program that solves this problem. So the problem is new to me and new to you. So you have to think about how you solve it. But it often helps you come up with an algorithm that at least works based on this divide and conquer thinking. So given a problem, but somehow you divide the problem into similar subproblems. And if each subproblem is somehow solved, but this is simply accomplished by using recursive calls, then you are somehow able to combine them to get the result of the original input. So if this somehow works, then you get the algorithm, right? And so once you come up with the outline of the algorithm, well, it is actually easy to write a working program. Well, especially if you are familiar with recursive calls, just like I have shown here. So this is a recursive call to the same function. And so once you get this kind of formulation, it is often easy to parallelize. So especially when you are familiar with task parallelism. Well, it's not always the case, but it's in many cases true that, okay, so once you formulate the problem into in this way, you then discover that these problems can be solved in parallel. Well, so it's not always the case. I'm not saying it's always the case, but it's often that, okay, these problems are somehow disjoint. So in terms of the data structure, you have to deal with. So there's no issue in doing all of them in parallel. So once you get this formulation, all you have to do to parallelize this algorithm is to call these recursive calls in parallel. So this can be straightforwardly done with something called a task parallelism. We've discussed before. Well, I'll get to that shortly again. And moreover, well, so I cannot speak too much about this, but so if you formulate the algorithm in this way, it often has a good locality of reference, both in serial and parallel execution. So again, I'm not saying this is always the case or this is necessarily the case, but well, if you formulate the algorithm in this way, well, so this part and this part tends to work on different parts of the data. So the locality tends to be good. So yeah, in many senses, I have just described and mastering this paradigm of divide and conquer, and mastering the task parallelism to parallelize divide and conquer algorithm are very important. So here are some examples. Actually, I asked a question like this in very earlier exercise, but what some examples that can be formulated using divide and conquer. So I guess you are familiar with a quick sort and merge sort. This is for what you are going to experiment with later today. And matrix multiply. So this is typically expressed in just a triply nested loop, but actually you can formulate it as a divide and conquer algorithm. The matrix multiplication of a larger matrix can be just divided into several sub-matrices, and the entire result can be obtained by the result of the multiplication of these sub-matrices. So it is actually possible, quite possible to formulate matrix multiplication using divide and conquer. And it actually has the locality benefit. So LU factorization is essentially an algorithm that solves linear systems of equations. Well, so if you are asked to solve this problem without knowing how you do it, well, so it's not a trivial matter, or especially when you ask to do it in parallel. But if you become somehow familiar with the divide and conquer paradigm, it's quite natural. So you can naturally derive working algorithms for LU factorization. I'll get to that in the later in this talk. So FFT, polynomial multiplication, big integer multiplication, they are very similar things, but they can all be naturally expressed using divide and conquer. Well, there's some other where some are less important, but are still interesting algorithms like maximal segment sum and find a median that were not easy to come up with the solution of. But if you try to think in terms of divide and conquer, so you may be able to come up with an algorithm. I'm not going to get to this later, but well, if you are interested, just Google it. So KD tree is something I'm gonna get somewhat depth using as a specific example. So I'll get to this next. So let me talk a specific example of something called the KD tree construction. But to demonstrate that even if you are not familiar with this problem at all, or if you was advised to think in terms of divide and conquer, you may be able to come up with a good algorithm. So I'm not necessarily saying this particular problem is super important, but it's important in the sense that this is a good example with which you can understand the benefit or importance of the divide and conquer thinking. So what is a KD tree anyways? So it is a data structure to hierarchically organize points in what 2D or 3D spacing typically. So theoretically, you can think of these points being in more higher dimensional space, 4D, 5D or more. But in practice, the KD tree is most beneficial for relatively low dimensions like 2D or 3D. And this is primarily used for searching for points near the specified point, or searching for the point closest to a specified point. So just whether these red are the points, so you are somehow maintaining, and you are given another point and asked to answer points around the specified point. This is a situation in which KD tree is useful. And more specifically, it is a tree structure. Well, so the name suggests it is a tree structure. And this is a 2D example, obviously. And the entire tree or the root of the tree represent the entire space containing all the points you are maintaining. And because this is a tree structure, each node, except for leaf nodes, has children. So the KD tree is more specifically a binary tree. So each internal node has up to 2 children. So in this specific example, this root node has 2 children. So one child is this one, so left one is split by this vertical line. And the other child is obviously this one, right? And for example, this left child of the root has again 2 children. So one is this one, and the other is this one. So you simply repeat this until a single node becomes small enough, small in the sense that it does not have too many points. Right, so you can, so I guess you get it. So this represents a tree structure. So this is the root, and the left one is a child, and it has 2 children. So one is this, and this guy again has 2 children. So the one is this one, and the other is this one. So you simply repeat this splitting. So you split it vertically first, then horizontally, and again vertically, or something like that. And so the algorithm we are trying to think about is how to build such a tree given the set of points. So more specifically, the input is P and R. So P is an array of points. So points are not ordered in any particular way. So it's just a set, essentially. And you are also given another input, which is the bounding box of P. So going back to the previous slide. So you are given all these red points as P, and the entire bounding box like this as R. So you are given these 2. And you're supposed to build a tree that was illustrated in the last slide. So it is a KD tree for P. So what are the valid KD tree needs to satisfy? So here is the list of properties of any KD tree. So one is a leaf node has at most a C point. So if there are too many points in the node, then you have to keep splitting. The second one is an internal node, well, a node that has children. has a one point of its own through which this internal node is split. So this node belongs to this internal node. So not any of these two children. So an internal has one point of its own. So plus one or two children. So in some cases, it may happen that you don't have, for example, left children because there are no points somehow the left of this point. So it in general has one or two children. So each internal node is split into two subspaces through its own point, like this. And so when you say, okay, so you split this particular node into two, well, you can split it either vertically or horizontally. So the way you do it, so how you choose either horizontally or vertically. So you can do it in several ways. But here we simply alternate between horizontal and vertical splitting. So in the beginning, you split it in vertically, then horizontally, then vertically, and then horizontally. So well, you could do somewhat more sophisticated ways, but for now, just for the sake of simplicity. So here is the problem of how you actually build a KD tree. So just think for a moment. So if you are asked to do this, so without knowing the algorithm, so without having a textbook, how do you do that? So one possible strategy is something called an insertion-based method. So somehow define a method to add a single point into a tree. Okay, so you can imagine you can at least do that, right? So for example, if you are already if you have already built a tree like this, okay, let's consider just adding another point here. Then well, so somehow you traverse a tree from the root to a leaf, right? And so when you reach a leaf somehow overflows, right? Which means that the number of points in that leaf becomes larger than the threshold. Then you split the leaf into two. Well, you can do something along this line. But well, so once you have an algorithm for adding a single point into a tree, then you simply start from an empty tree and add all points into it. Well, that's one way you can do it. But when it comes to how you do it in parallel, I think it's going to be somewhat challenging. It's going to be challenging to make it fast because there's so many threads trying to insert points, or especially but near the root of the tree, then there will be lots of contentions. Where if you do it using mutex lock, I probably there will be no speed up. So, of course, there may be some situations you have to build a tree in this way. So, for example, when you are actually asked to incrementally build a tree, when all the inputs are not necessarily available from the beginning, you may have to do it in any ways. But here, let's consider a situation if it's basically you are given the entire set of points from the beginning, and how to do it more specific, how to do it more efficiently. So like I said in the beginning, so well, a divide and conquer method or divide and conquer thinking helps you come up with a very natural and efficient algorithm. So this is how you do it in divide and conquer strategy. So you are given the set of the bounding box R and points, the set of points P in this bounding box R. So you are asked to build a tree that represents this P. Also, divide and conquer thinking simply tries to think something like this. Okay, so you simply get all the points left of some vertical line. Well, how you choose this vertical line is one thing, but let's assume that for a second, we have already somehow determined the vertical line with which we split the entire space. Then, yeah, all you need to do is just collect all the points that should go into the left child and right child. So once you have set things up in this way, you simply make a recursive call, subproblem solve to build a KD tree that represents this left half, well, not necessarily half, the left part, and also the right part. And then what the entire result is simply a node having these two subtrees as its children, right? So if you think in terms of divide and conquer, it's actually very simple or almost trivial. So more specifically, you simply choose a point P, well, any point actually. Well, so I'll get to that. What is the a better way to choose this P, but well, just choose any P through which to split R. And then just partition the original set of P, of the points P, into all the points left of this chosen point and all the points right of this chosen point, like this. So in the original the array P, well, points left and right of this the chosen point appear in no particular pattern, right? But you simply collect all points left or collect all points right and arrange them in this way. Then you simply make a recursive call. Just make a KD tree for these points and make another KD tree for these points. And you simply make a node that has these as children. Right? So that it's as simple as this, right? So in terms of the program, it looks as simple as this. So this is the KD tree construction algorithm. Let's name it the build. Build is given the set of points P and the bounding box R. And just to determine along which direction, either horizontally or vertically, we split the rectangle, the bounding box. Just it is given another integer parameter, the depth. The depth is used only to determine whether we split horizontally or vertically. So if P is an empty set, then essentially it returns nothing. Well, it's an empty tree. Well, let's assume that 0 represents an empty tree. and the number of points in P is less than predetermined threshold, then yeah, we just make a leaf containing all the points given. And otherwise, well, so it just does what I have just described. So find a point through which we split the rectangle. So let's call it a find median. And we get a point through which we split the R. And well, this is the, okay, so this split left is simply to make two smaller bounding boxes. So bounding box for the left child and the bounding box for right child, and let's call them R0 and R1. And this is actually the main part. So P originally has all the points in R in no particular order, or there's no relationship between the geometrical location of each point and the location in the array. So we partition P so that all points, so when we are splitting it vertically, then all points left of the chosen point S will come the first half of the array, and all the points right of S come after that. So this is the partition. So this is very similar to what you will be very familiar with in quicksort algorithm, right? And we simply call this build recursively twice. So one for the left one and the other for the right one. And you simply make a node, make an internal node, and that has P as its own point, and N0 and N1 were children as its children. So that's about it. And well, of course, we have to work out the details of these find median and split left and partition, but this is not well particularly difficult. So find median is simply picking a point in P. But there's actually a similar issue with how to choose the pivot in quicksort algorithm. So you wish to pick a point that is somehow near the center of the rectangle. Right? So not necessarily center. We like to pick a point for which the number of points left of it and the number of points right of it approximately the same. So this is how you want to choose the this pivot. But actually, so trying to find the best point, well, actually takes time. So that does not make much point. So in practice, you simply sample a few points and choose the point that is middle. So this can be done in a constant amount of time. So this is, well, again, very similar to what we usually do in quicksort. And split left is, well, it's actually very straightforward. So you simply build the data structure that represents the left rectangle and the right rectangle, or the top and bottom parts. And partition is actually the important part. So you are given many points, and with these parameters that the dimension. For example, if this is 0, let's call it a dimension that represents a vertical split. And C is the coordinate of the chosen point. So basically, this partition collect all the points whose this coordinate is less than c to the first half of the first part of the p, and collect all the points whose this coordinate is larger than c, the second part of the p. So this takes time proportional to the number of points in p. Well, a fact that becomes important later. But just in terms of how you implement them correctly, I don't think there's any profoundly difficult issue here. So yeah, again, so I'm not necessarily saying that the KD tree construction is a super important algorithm. You have to somehow remember. So I'm just discussing it as an example for which divide and conquer thinking helps you come up with efficient and natural algorithm and simple algorithm. So there are so many other examples for which divide and conquer formulation helps. And the next section is, so then, okay, so you get divide and conquer algorithm, and it's recursive. So its implementation in terms of the program using recursions, and then how to do it in parallel, how to parallelize such algorithms. But actually, it's not that difficult. So divide and conquer algorithms are typically very simple and easy to parallelize if the programming language or library supports asynchronous recursive calls or parallel recursive calls. And well, it is a case in programming language supporting something called the task parallelism. And we discussed this before in very early weeks. So specifically, the OpenMP task parallel construct. So well, just to refresh your memory. So what you need to master is this hash pragma OMP parallel master task and task wait. So I'll get to it now shortly. And actually, there are some other parallel programming libraries or languages that support similar concepts, such as Intel TBB or Silicon C++. But in this lecture, all you need to use is this OpenP. So this is simply how the algorithm we have just arrived at can be parallelized using OpenP task parallelism. So just to refresh your memory, so this pragma OMP task is a construct with which you can say, okay, so please do the following statement concurrently with the caller, whoever calls it. So what happens with this pragma is, so while this recursive call to build is taking place, the caller actually moves ahead. And the caller then makes another task creation, and that does this another recursive call. So the end result is you have two tasks running concurrently. So each of them doing a recursive call to build. So you effectively call these two recursive calls in parallel. And then you simply say task wait. So you wanna wait for these two recursive calls to finish. And another, one detail that I haven't mentioned is this shared N0. So the shared N0 means that this variable N0 is shared between the created task and the parent. So if the created task assigns to this variable n0, then it becomes visible to the parent too, just because of this shared n0 clause. So similarly for this shared n1. So after you wait for the completion of these tasks, then you are able to safely use these variables n0 and n1 here. So you simply make an internal node having n0 and n1 as children. So this is very straightforward, right? And also, the one thing I have to note is that it's very difficult to parallelize this algorithm solely with few parallel loops, right? So task parallelism is actually a very important construct for general purpose programming languages. So this is basically what you have to you have to master for today's experiments. Okay, so I'll get to the next topic after you played with a notebook. So in this today's notebook, you're gonna parallelize and merge solve. I think you are already, many of you are already familiar with merge solve, but even if you are not, you can easily understand how it works. So let's have some time to do it. So I got a question. So do you have an example that it doesn't have good reference already? Well, so it's a bit difficult to answer. So difficult to answer partly because whether it has a good locality or not is already somewhat subjective. But but just to that straightforward answer to your question. So I don't come up with any on top of my head at this point. So basically, at least when we are talking about parallelizable divide and conquer algorithms, it is often the case that each subproblem call tends to work on different parts of the data structure. So by definition, the locality of difference is pretty good already. Okay. So let's do this exercise. So there should be a new notebook called PD11. It is about divide and conquer. The specific topic is merge solve. And if you think you already forgot about task parallelism in OpenP, just check this slide again, this part. So this index may be somewhat upload. Yeah. So just check this slide again. So one thing you have to be very careful about is, so there must be enclosing OMP parallel construct, and immediately below the OMP parallel construct, you have to say OMP master, so that this top level call is done only by the master, or only by one single thread. And if you create tasks later, then these tasks will be distributed to other workers. This is how task parallelism basically works in OpenP. So do not forget this. Okay, so let's do it until 6 o'clock. And because the end of semester is approaching, if you have some questions about anything, so how the final report is supposed to look or anything else, you can ask in this opportunity. So I got a question about the final report. So in the option 1, yeah, I was not necessarily very clear about whether you are supposed to work on only CPU, only GPU, or both. So the thing is, well, you can choose one. So you don't have to do both. But if you if you do both, then yeah, of course it's great. But that's so I will clarify. Yeah, for what kind of things appreciated later in writing, but it's in a way, yeah, obvious. The bottom lines, you don't have to do both. Yeah, but yes, if you do both, then it's appreciated. Okay, and keep small. Okay, let's get started again. So, so you can work on that later if you haven't finished it yet. But the first part of this exercise is we're just trying to convince you that the divide and conquer is a relatively simple paradigm, and parallelizing it is very simple. But once you have a task parallel concept. So just in case you are not familiar with merge sort, this is how it actually works. But I think it's instructive to just imagine that you are asked to sort an array without knowing any sorting algorithm. Just try to think in terms of divide and conquer paradigm. So the way your thinking goes is, okay, so you are asked to sort an array by using divide and conquer paradigm. You simply, do, split the array into two parts. So I'll try just have two almost equal halves. Sort them individually. So now you have two sorted arrays. All you have to do is just to somehow merge two sorted arrays, right? If you come up with some way to merge two sorted arrays, then you are done, right? So this is exactly what this msort function is doing. So you simply make a point, middle of P and Q. So P is the start and Q is the end. And you simply solve the first part. Well, so you have to figure out what each of these parameters actually exactly means. But basically, this is sorting the first part. And this is sorting the second part. So now you get two sorted segments. All you have to do is just to merge these two sorted segments. And how you actually merge these two sorted segments is written elsewhere. So this is what this merge procedure looks like. So you can look into this, but the basic idea is very simple, right? And if you are asked to parallelize this, then all you actually have to do is only this. So you have OMP task just in front of one recursive call, and another OMP task in front of the other recursive call, and then say, okay, I want to wait for these two recursive calls to finish. The another subtle point is, so before you make this function call to sort the entire array, you have to do this OMP parallel to launch a number of threads And immediately after that, you say, okay, so this particular recursive call should be done exactly by the master or the single thread. So this is what this OMP master is for. Okay, so that's it. And you can parallelize it, and you get a result that looks like this. So this is the speed up curve up to 32 OpenMP threads. So you get, well, in a way, only 8 or something like 8 or 9 factor of speed up, a factor of 8 or 9 times speed up. Well, this is not necessarily very satisfactory, and I'll get to why and how to fix it in the second part of my talk. But that's basically it for now. Let's resume the talk. So, okay, so this leads to the next very important and somewhat profound topic of how to reason about the speed up of task parallel programs or divide and conquer, parallel divide and conquer algorithms. So yes, the context is just like we have witnessed. So you parallelize your program using task parallel primitives, which is hopefully very easy. So you now hope to get some speed up of parallel machines. But the problem is, okay, how to reason about the execution time or equivalently the speed up of the program when you are using P processors. So we just witnessed that, okay, so this program making these two recursive calls in parallel only get something like a factor of 8 speed up with 32 processors. So is there anything wrong with it, or no? That's the question, right? Of course, very intuitively, 8 times speed up using 32 processors is not very satisfactory. So you want to do something about it, right? But how? Well, so this requires a somewhat firm understanding about what kind of speed up you should expect from task parallel programs. Well, actually, there's an elegant answer for this. So so that the master the notion of work and critical path length of the computation. So which is exactly the topic of this section. But before moving further, so let me just remind you of where we stand. So the reasoning about this task parallel programs, it is not as easy as, it is not as straightforward as reasoning about the performance of a simple parallel for loop. Because, okay, so just let's recall that the structure of the program is something like this, as I have shown in the beginning. So each of these recursive calls will be made as a parallel task, right? So using OpenMP task. So they can run in parallel with each other. So the same is true for these tasks, right? So you end up with creating much more tasks than the number of cores, right? And these tasks are generated along the way. So it's not as simple as, okay, so you have a for loop that iterates million times, and you have 10 cores, and each core gets something like 100,000 iterations. It's not as simple as this, right? So you actually in the beginning don't even know how many tasks will be generated along the way, right? So it all depends on the input data. So it depends on, okay, so when the recursion stops. And in the case of, for example, KD3, the recursion stops when there's only a small number of points in the given region. Right? So when exactly this happens, it's not easy to predict, right? So executing task parallel programs is actually much more complex and requires much more sophisticated machinery than just executing a simple parallel for looping, which only amounts to distributing iterations to whatever number of cores you have at the beginning, right? So reasoning about the speed up of task parallel program is not necessarily very easy. So that's why we are getting into this. And like I just suggested, there are two important concepts called work and critical path lengths. They are very, they have very specific technical meaning in this context. So work is the total amount of work of the computation. So it is equivalent to the time it will take in serial execution. So it's actually exactly the same as so-called time complexity of the algorithms, right? So we always talk about the time complexity of algorithms, right? So quick sort has the time complexity of order n log n, merge sort has n log n. So matrix multiplication and cubic, for example, when the matrix size is n by n, right? So this is in a way the serial time complexity, the work, but in the context of parallel computing, or just to distinguish it from something else, so we say we call it the work, the total amount of work. The other, perhaps more important in the context of reasoning about the speed up, is this critical path length, which is the maximum length of dependent chain of computation. We'll come to that later using illustration. So a more precise definition for this, the notion of something called computational DAG. So here's the concept of computational DAGs. So DAG means directed acyclic graph. So that stands for directed acyclic graph. So DAG of a computation is a directed acyclic graph in which a node is interval of computation that does not have any task parallel operation. So just imagine it as a sequential computation. So a single node starts and ends by a task parallel. So for example, when you originally have a main task, so you do something inside A. So let's assume A does not have any task creation or whatsoever. Then this execution of A becomes a node of the computational DAG. And this A ends when you perform some task primitives. So let's say, okay, right after A, you create a task. Well, this is exactly what OMP task, so Pragma OMP task does. Well, let's write it in a pseudocode-like fashion in create task, with create task. So So the node ends when you create a task, right? This is a node in the computational DAG. And the edge in the computational DAG represents a dependency between two nodes. Well, actually, there are three specific types, but well, in generally speaking, a dependency like this represents the relationship between two nodes that determine the order these two nodes must be executed. So more specifically, when there is an edge from A to B, it means that B can start only after A is finished. So this is exactly what dependency actually means in general in computing. Right? So in the case of task parallel programs we are talking about, but the dependency results in one of the following three ways. So one is, okay, so there's a parent and a created child, right, like this, right? So B is created by, well, after A. So there's a dependency between from A and B. So more specifically from A to B. So which basically represents in this program, there's no way you can start B while A is still not finished. Because you create B here after A is finished. So this actually represents the fact that B is created only after A is done. So there's another way this dependency is created, so which is from a child to the waiting parent. So this is the dependency between B and B here. So going back to the original program, the parent, after creating B, does C and wait for the completion of B, after which it performs D. So which means that there's no way you can start doing D before B is finished, right? So because you are waiting for B to finish here. So there's an edge between B and D, so more specifically from B to D. Similarly, there's an edge from C to D. So this is the third bullet. So from one node to the next node in the same task. Well, simply, so A, C, and D are all in the same task, right? The parent task. But so in each task, the things happen sequentially. So A, then after C, then after well, A, after A, then C, after C, then D, right? So there's always a dependency between computations that happen in the same task, right? Like this. So this is the computational DAG of the computation that will result by executing this program. So this is computational DAGs we are talking about. So this is going to be a very important concept when you reason about the speed up of task parallel programs. And so I'm getting to the definition of the critical path lengths, which is perhaps the single most important concept in this lecture. So let's consider each node is somehow augmented with a time for processor to execute it. So it is in this picture represented by the length of the height of each node, or the length of these red bars. So let's imagine the length represents the time taken for a single processor to execute each node. So let's call it the node's execution time, the execution time of the particular node. Then let's define the length of a path. The length of a path to be simply the sum of execution time of the node, of the nodes on the path. So for example, this is a path, A to B to D. So the path is a series of nodes connected, all connected by a dependency, right? So this is a path, and the length of this particular path, A, B, D, is the total execution time of A, B, and D. This is as simple as this. So this is the important definition. So given a computation of that, the critical path length of this particular DAC is the length of the longest paths from the start node to the end node in the DAC. So in this particular computational DAC, there are actually two paths, right? So from the beginning to the end. So this is the beginning of the computation. And I'm sorry. So I should have removed this clock. Sorry, I wasn't looking at it. So this is the beginning of the entire computation. And this is the end of the entire computation. And there are two pathways from the beginning of the computation to the end of the computation, which are ABD and ACD. And the critical path length of the entire graph is whichever is the longest, whichever is the longer between the two. So in this case, if we say the length of each node, the height of each node represents the execution time of a particular node, then the critical path is the sum of these three red paths. Right, so this is the critical path, critical path length. Well, to be precise, I think we should say critical path length, but we often simply say critical path, but to mean actually the length of it. Okay, so for any question? So this is the single most important concept. So as I said earlier, there's one thing else. So what is work? So we have defined the critical path. That the work is similarly defined in terms of the computational data. So work is simply the sum of all nodes in the computational data. Like I said, work basically represents the total amount of work, and that is represented by a computational data. So it's natural to define work as the sum of all nodes, execution times of all nodes. Okay, so this is, to be precise, the definition of work of a particular computational data. So what do they intuitively mean? So work and critical path, look somewhat different, but they are actually related in a very elegant way. Both are actually important in its own right. So the first, the critical path, or the critical path length, to be more precise, well, it represents sort of the ideal execution time if you are given infinitely many processors. Okay, so do you get that? So why? So even if you have infinitely many processors, millions of processors, there's no way you can, for example, do A and B in parallel, right? So because there's a dependency. So no matter how many execution resources or the processors, to be more specifically, you have, you cannot execute the entire graph shorter than the execution time of A plus B plus D, right? Because of the dependency. So the critical path intuitively means, okay, so of course it's the precise definition is already very simple, but to connect it into to connect it to something else, it's the execution time in a hypothetical environment in which you have infinitely many processes, infinitely many processes. Okay, so this is what the critical path actually means in more intuitive terms. So therefore, we often denote it by T infinity. So infinity means, okay, so you have infinite number of processes. So analogously, we often denote work by T1 because obviously, so work actually represents the execution time by an environment in which you have only one processor, right? So that processor has to execute all of these nodes. So obviously, the time it takes to execute the entire graph is simply the summation of execution times of all nodes, right? Which is work, right? So to signify that this is the time that a single processor would take, or it is often denoted by T1. So T1 is work, T infinity is the critical path. So why are they important? So now you understand what the critical path is. So the next important question is why is it a good tool, a good metric to understand the speed up? So here's a very elegant answer to this question. Okay, so well, I'm just rephrasing the question. So specifically, what does it tell us about the performance or speed up on, say, my 64-core machine? So you have T infinity, which represent the execution time in the hypothetically infinitely many processors, right? But what does it tell us about the execution time with a specific number of processors, like 64 cores? Right? That is a question we like to answer. So answer is, well, there's very elegant theorem called greedy scheduler theorem. So this gives us a very elegant answer to this question. So just given T1 and T infinity, you can have a fairly good approximation of the execution time using a particular number of processors, let's say P processors. This is what I talk about next. So greedy scheduler theorem. So here are some assumptions for technical assumptions we have to make. Of course, there's some gap between what this theorem predicts and what actually happens on the real machines. The real machines is much more complex than what we are going to assume here. But just for the purpose of clarifying the clear technical discussion, let's assume, let's make the assumptions very clear. So you have P processors, and these P processors work greedily. So which means that a processor is always busy doing a task. It is always busy doing a task whenever there's any runnable task. Runnable task means a task whose dependency has already been resolved. For example, going back to this computational DAG, B becomes runnable only after A is finished, right? So all tasks are not necessarily runnable all the time. So let's get back to the definition again. So schedulers or the set of processors are said to be greedy when, okay, so whenever there is a runnable task, so whenever there is a processor, that processor is already busy on another task, or well, so let me start over. So yeah, I think you can read it by yourself. But well, the greedy means that there's no time during the execution in which, but a processor is not doing anything. So it is not working on a task, even if there is a runnable task. But this is another way of saying the scheduler is greedy. Did you get that? So when in very intuitive terms, all processors try hard to find a task to work on. And whenever there is one runnable task, then where some processor will pick up and work on it. Well, this is the definition of the greedy scheduler. Well, generally speaking, this is what naturally happens when the processors try to do something useful as much as possible, right? So this is the second assumption. And the third assumption is that each task takes the same amount of time, no matter who executed. But this is in a way, well, so one thing is, well, this is somehow assuming that all processors look alike, but no particular processor is much more powerful than the other. But actually, the more important implicit assumption here is that it is sort of ignoring the effect of caches, for example. So for example, when particular data is on the cache of a particular processor, this particular processor is able to execute that particular task faster than the others. But when in this technical discussion, we are assuming that this is not this is not the case. So all the processors take exactly the same amount of time, no matter which tasks are executed by which particular processor. Now, I'm not saying this is practically true, but this is the technical assumption that is made when we discuss this very elegant greedy scheduler theorem. Okay, so here are the assumptions. So the theorem says that so given a computational DAG of work T1 and critical path length T infinity, then the execution time with P processors, or denoted by TP, satisfies this inequality. So TP, the execution time with TP processors, is upper bounded by, well, this is somewhat a complex term, but I simplified a little bit. So so this term is, well, so it's not super important if T1 is much larger than T infinity. So we often write it in a slightly simpler form. So this is actually the tighter upper bound, but we often write it in a simpler form. So T1 over P plus T infinity. So this is very important theorem. So it basically says that, okay, so as long as the scheduler is greedy, so all processors are trying hard to find a task to work on. So find a random task to work on. Then the execution time using P processors is guaranteed to be lower or equal to T1 over P plus T infinity. So the execution time of a potentially very complex task can be characterized by this very simple expression. That is actually very remarkable, right? So this is the source of greedy scheduler theorem. So it is, well, in a way, it's something that every professional in parallel computing is familiar with. But the root of this theorem seems this very ancient paper. And so people seems to be attributing it to this the author of this paper and call it brain theorem. And mathematical proofs. So you can mathematically prove it, well, given these simplifying assumptions. And I think it is a good exercise. We can discuss the proof in next week if you like. But for now, it's to you. And yeah, why this is so important and why this is so useful and how this is how you can remember if you think it's a bit still complicated the expression. So here are some ways to remember that. But I think it's already past 35. So let's continue discussing this in the next week. And so what we are going to do in the next week is, you understand this theory, and we take another look at, for example, KD3 algorithm we discussed before, merge sort algorithm you have just worked on, and analyze this T1 and T infinity and reason about the speed up. And with that, you can kind of understand why the parallel, the speed up is not very satisfactory with this merge sort algorithm. And through going through this analysis, you have also some ideas about how to make it more scalable. And this is the topic we are going to get into the next week. So with that, I think I will finish it for today.